Welcome to Lecture 16A. This is a series of 3 lectures on triple integrals in spherical coordinates. So in this first lecture, we'll deal with just the details of performing integration triple integrals in spherical coordinates, followed by examples in Lectures 16A, 16B, and 16C. So the material in this lecture comes from section 16.5 of the text. And reading assignment 2, reference material from section 3.2. You're not required to look at the material. It might just be useful to look at, but again, not mandatory. So the objectives of this lecture are to develop the tools for sketching and computing triple integrals in spherical coordinates. And the concepts and visualization skills obtained from this lecture would be the integration bounds for radius rho, angle phi, and angle theta. Visualization of bounding surfaces in spherical coordinates. Again, a reminder that any volume is basically bound by 6 primitive surfaces. And thirdly, the differential volume in spherical coordinates. As usual, the second slide is just a summary of the slides to follow, and so we'll just move on. All right, so spherical coordinates basically have this particular property. You basically have a line that basically points from the origin to some arbitrary point, P, and its coordinates in spherical coordinates are rho, psi, and theta. And the range on rho is between 0 and infinity. The range on psi would be from 0 to pi maximum. Of course, it could be less than pi, but that's the maximum value psi can attain. And the value of theta will range from 0 to 2 pi. Theta is basically taken in the counterclockwise direction in the xy plane from x moving in a counterclockwise direction. And so this is basically from in this direction. Psi, on the other hand, is an angle that's measured from the z-axis downwards towards the xy plane. And so this is the direction for psi. So psi of pi would take you basically all the way to the minus z-axis. All right, so just a couple of things here. The coordinate rho, it's pronounced rho in spherical coordinates, should not be confused with r in cylindrical coordinates, which is a distance from P to the z-axis. In cylindrical coordinates, r was measured in the xy plane. In spherical coordinates, rho is measured to any point x, y, z in 3 dimensions. But again, since we're using spherical coordinates, the coordinates are being used here now with respect to rho, psi, and theta. Rho being the distance measured outwards. Secondly, the coordinate psi is called the colatitude because it is pi over 2 minus the latitude of points in the northern hemisphere. Now this is an important point, and it'll come up more often than not. The physicists may reverse the roles of theta and psi. That is, theta is a colatitude and psi is a polar angle. Be very careful that you basically don't start memorizing labels. What's important to realize is whatever label is used to basically define what's happening on the xy axis must be counterclockwise. Whatever label is used to define what's happening from the z-axis down to xy, that defines the label that's used for that. As long as we stick to that convention, then basically we're guaranteed to have a right-handed coordinate system. Now, one other point is that later in this course, we will replace rho with r, since rho is used to define a scalar density. So get used to the fact that we'll be using different symbols under different circumstances, but to make sure that you always obey the right-handed convention. All right, if you want a demonstration of this for different values of psi and theta and rho, then you can access this URL. And maybe get a better understanding of what the different parameters will do. All right, so now we look at the actual coordinate transformations. Remember that when we take transformations, we're interested in basically determining how x, y, and z are related to the new coordinates. And we need that information because that allows us to establish the Jacobian. And the Jacobian will allow us basically to define what is the differential volume look like in spherical coordinates. On the other hand, if we want to understand what the boundary is, then we need basically to have rectangular circle, which means that on this side we have all of the variables associated with spherical coordinates, And on this side, we have all the variables associated with the Cartesian coordinates. So we need this type of formulation to establish the boundary values in the new coordinate system. And we need this transformation to establish the Jacobian, which allows us to determine what the differential volume is in the new coordinate system. So this would be your transformation matrix T. And this would be the, sorry, not matrix, but transformation T. This would be your transformation T inverse. As far as the details here, what the transformations would look like. So this being rho and this being psi, then we can basically just use ordinary trigonometry. If we want to know the vertical height, which is z, that's just going to be rho times cosine phi. If we want to know the distance projected along the xy, in the xy plane, then that would just become rho sine phi. If we want to then determine what the x value is, then it's a projection of rho sine phi on the x-axis, which would involve cos theta, and then for the y-axis it would be rho sine phi sine theta. So this is basically a picture illustrating what these this transformation is actually performing. And again, everything now is in terms of the new variables, that is rho, psi, and theta. And the angles, again, according to right-hand convention, theta on the xy plane in the counterclockwise direction, and psi with respect to the z-axis going down. All right, so the next thing would be, if you're given various surfaces and you're going to do a calculation spherical coordinates, we need to transform the equations representing a surface into spherical coordinates. So we're going to look at some simple examples, in terms of how that is done. And so there'll be what we call three principal surfaces. So one would basically involve, a surface where you hold rho constant, a surface where basically you would hold phi constant, and a surface where you hold theta constant. So these are three examples to consider. So for instance, if rho is equal to a, right, and a is greater than 0, then what we're doing is we're just mapping out the surface of a sphere of radius a. Now the fact that phi and theta are not mentioned just implies that phi can be any value from 0 to pi, and theta can be any value from 0 to 2 pi. If you scan phi from 0 to pi and theta from 0 to 2 pi, then what are you doing? You're just mapping out the surface of that sphere of radius a. All right, what about if we hold phi constant at some value theta naught? So in that case, basically, we have a line that looks like this. Rho can be any value, and theta can be any value from 0 to 2 pi. So what are we doing is we're mapping out a cone, and this is the inclination angle. Now the value 0 and pi by 2 and pi are not mentioned because they're special cases. If psi equals 0, then this just becomes a straight line pointing in the z direction. If psi is equal to, psi naught is equal to pi over 2, you're talking basically about a plane in the xy plane. So that would be like saying z equals 0. If it's pi, it would be a line that's pointing downwards in the negative z direction. This is a principal surface because we're just holding one of the variables constant. All right, what about if we hold theta constant, some value theta naught? In that case, rho can be any value from 0 to infinity, and psi can be any angle between 0 and phi. So in that case, basically, phi could be here, here, all the way down to here, and rho basically, which is measured with respect to the origin, can point from 0 to infinity. So effectively, we are mapping out a half plane, and that orientation, the orientation of that half plane would be this angle theta naught that you see here. All right, then we have another example. What about a horizontal plane that is at z equals a? So in this case, we'll need to use a little bit of trigonometry. So here, for instance, this rho basically would be pointing to any point on this flat plane. And basically, the distance from the origin to the plane vertically is going to be a. And this angle is psi. So we can relate rho, the angle psi, and a to each other. It's just rho cosine psi is equal to a. But we want rho, so we would just have to bring cosine theta, cosine psi to the other side, and so you end up with rho is equal to a sec phi. Now what about the values of psi in this case? Well, the psi basically can only go from 0 to pi by 2. At pi by 2, this would be pointing in this direction. And the angle theta, of course, would be from 0 to 2 pi, and so you would be mapping out this infinite plane located at z equals a. If a is less than 0, that means we're below the surface, right? It'll be a flat plane below the surface. The only thing now is that the angle would change. The angle would be from pi over 2 to pi, which means down here, below the xy plane. And so this is an example for a horizontal plane. All right, let's take two more examples. What about an infinite cylinder of radius a? Well, in this case, we would have to construct a row that points to the surface of the cylinder of radius a. This is the angle psi that you see here. We know that if this is a, then rho times sine phi would be this dimension, which is a, or bringing sine phi to the other side, this would be rho equals a cosec phi. All right, we want to scan the whole length of the cylinder, so that means this angle psi goes from 0 all the way to pi. And so theta, of course, will be from 0 to 2 pi. Why? Because theta is not mentioned, which means it's implied that the full range of theta is being utilized. And lastly, we have the case of a sphere of radius a that's offset by a distance a, which means that it's just touching the origin on the xy plane here. So in this case, we have to set up rho, again, with respect to the origin, to point to every point on the surface of the sphere. This distance is a, this distance is a, and this angle in here is cosine phi. So we can use the cosine law for triangles to basically relate the length of this to the length of this, and the cosine angle between these two, which is what I've written out here. The a scales will cancel, and then I can factor rho out, and finally you end up with this is equal to 0. And so the only suitable solution is when rho is equal to 2a cos phi, which is what we see here. And the angle psi will range between 0 and pi by 2. You can see when this basically comes down to this point, it's lying flat, which is an angle of 90 degrees. And of course, because theta is not mentioned, it's implied that theta ranges from 0 to 2 pi. So that allows us to scan the surface of the sphere offset by a units with a radius of a. So these are some simple examples in terms of how to characterize various surfaces, but in spherical coordinates. All right, so now we end up with the actual physical theorem. And again, we start with the Riemann sum when we're doing a triple integral. So let's assume that fx, y, z is a mass density, which case its units are kilograms per cubic meter. So when we formulate the total mass, we would say that this is the mass density, but x, y, and z now are replaced by the transformed system of equations. So this is the equivalent transform for x in terms of rho, psi, and theta. This is for y in terms of rho, phi, and theta, and this is in terms of z for rho and psi. And so this star indicates that you're evaluating the value in the center of the small differential volume. And so the differential volume you're pointing to is indicated by the subscript k. And delta k is basically the differential volume of the kth volume element. So if you take the number of volume elements, right, and increase them to infinity, which means each one of these volume elements go to 0, then in the limit, this becomes the triple integral of fx, y, z dv. And in this case, dv takes on this form, rho squared sine phi d rho d phi d theta. And this is then delta vk that would have gone in the expression here. All right, so let's look at then the general theorem dealing with change of variables for triple integrals in spherical coordinates. Let f be continuous over the region D, expressed in spherical coordinates as in this form. Now notice here, we've got a is less than or equal to psi is less than or equal to b. So these, for this case, the psi is in terms of constants. That doesn't necessarily have to be the case. It could actually also be, the middle integral could also have bounds which are a function of theta. It'd be a little bit more difficult probably to do such computations, but it's doable. They only treat this case here, but there is a theorem that would allow these things to be functions of theta. So if you look carefully at this, the x has been replaced by the x coordinate for the spherical coordinates. This is the spherical coordinate representation for y, and this is the spherical coordinate representation for z. And this is the differential volume when we're talking about spherical coordinates. The first integral with respect to rho, and so that means the upper and lower bound would have to be functions of psi and theta. The next one with respect to phi, here it's in terms of constant angles A and B, but these could be actually functions of theta as well. The last one is with respect to d theta or theta. These are always going to be fixed values, so these would be a lower bound on angle theta and an upper bound on angle theta. All right, so just a couple pictures here basically describing the differential volume in spherical coordinates. Let's first look at how the computation of the differential volume takes place. So dx, y, dz would transform into the absolute value of the determinant of the Jacobian matrix. As we mentioned before, if you're dealing with a right-handed coordinate system, then the determinant will always be positive. In this case, it will be positive. When you set up the Jacobian matrix, the first row involves the partial derivatives of x with respect to rho phi theta, y with rho phi theta is the second row, and the partial derivative with respect to rho phi theta of z is for the third row. If you take the determinant of this, you basically have the values that you basically computed after taking partial derivatives, and this becomes rho squared sine phi d phi d phi d theta, d rho d phi d theta. So we've chosen a right-handed coordinate system, so this basically is a positive entity. There's no negative sign here. Just as sort of a note, it's useful to remember that the differential volume in spherical coordinates is rho squared sine phi d rho d phi d theta. It's handy to have that at hand when you're doing calculations involving spherical coordinates. So this is just a pictorial representation of the differential volume. You can basically say there's a delta rho in this direction. There's a delta phi in this direction. And then in this direction, you basically would have to take a projection of this along this direction. And so that basically just becomes rho k sine phi k. So the rho k sine phi k would be this length that you see here. And then that rho sine phi times delta theta would give you the third side. If you multiply the three of them together, you end up basically with this being the differential volume. Now, spherical coordinate systems, the actual directions are orthogonal with respect to each other, and so in the limit, this is just a very small rectangular box. Okay, so you can basically look at this in more detail if you wish, but that's basically just sort of a pictorial description of interpretation of a differential volume in spherical coordinates. All right, you can also do a look at the interactive demonstration of a differential volume in spherical coordinates at this URL. We also have an interactive demonstration of integration boundaries in spherical coordinates. Again, you can look at this URL. And this is just another example that you can look at. Just play with it. Try to get a good feeling as to what is happening. Help you to visualize. And this is just another example. These are the surface boundaries in spherical coordinates. In this example, the volume is bounded by the following 6 surfaces. The exterior surface with some inner radius g as a function of phi theta. The exterior surface with an outer radius h as a function of phi and theta. So this basically would represent just a section of the outer surface. And this below that you see shaded in blue would be the inner surface. All right, and 2 conical surfaces and 2 half planes. So here, for instance, you see one conical surface. That would be for angle phi equals A. And this is the other conical surface for phi equals B. So somewhere between these two cones is part of the region. And lastly, the 2 half planes. So one half plane would be here for some angle alpha measured with respect to x-axis, and half plane here, angle beta with respect to the x-axis. These are basically just showing small segments of it. And so between here and here would be the region. Between here and here would be the region. And between this surface and this surface would be the region. When you put the 6 surfaces together, everything inside basically is the domain of interest. Okay, so as far as integration steps in spherical coordinates, upper and lower bound on middle and outer integrals are constants for this particular example. So for example, the first one would be with respect to rho. So this would be inner surface, outer surface. So this will be the upper bound and lower bound on the innermost integral. So the second integral will be with respect to phi. So you'll be talking between phi equals a and phi equals b. So basically going from here to there. And lastly, we'll be looking at integration between an angle of theta of alpha, which is from here to here, and theta equals beta, which is from here to there. So that's the steps that we're doing. And in the process, what you're doing is you're mapping out that little volume contained between the 6 surfaces. Well, that concludes Lecture 16A. Thank you for listening.